Thank you very much, John, for that nice introduction. That was very kind. So like John, this is also my first time in this beautiful space and at BU, and it's fantastic to be here. I've had already a lot of fun talking to several of you, and you've been very hospitable and very kind. So I try to put together sort of a sample of some of the problems that my group focuses on, and I hope that you leave this with a couple of, if not all, a couple of things to take away from each of these elements and components that John was referring to. So I don't think I need to motivate the need, or rather the relevance of tools that are nowadays referred to as AI or artificial intelligence, and the way that they are impacting science and the way that we think about the world. You might have seen, apologies, you might have seen how methods are developed that can mimic human conversation, they can mimic human playing, they can help us devise algorithms to do things that we thought we knew how to do very well and very efficiently, like matrix multiplication operations and algorithms, or it can help us do things that we knew a little bit less about, like folding these very complicated chain of amino acids in space in these very complicated 3D protein structures, or developing chatbots that most people, I presume, in this room use. And indeed, this is for good reasons. We can do very good. We can do a few things very, very well now that we have access to some of these tools. So to begin with, I'm going to give you a very, very brief snapshot of things that we've been doing together with collaborators at Johns Hopkins on applying these things, these tools, to medical imaging in particular. And I'm not going to spend a lot of time in this. It's just to give you a snapshot of the kind of things that we do, but then I will move on to the rest of the talk. The first one has to do with collaborations that I have with colleagues in neuroscience through the Kavli Institute, for example. And when I talk to my colleagues in neuroscience, naturally the dream goal is to understand the brain. So it would be amazing if I had for example, an animal model, and it's a mouse, learning about neuroscience, and then I could be imaging the brain, and I would be able to detect and basically read what the mouse is reading and detect whether the mouse has learned something new. So some colleagues at Hopkins have been building on the technology to do this. They have very nice, basically 2 photon imaging systems that this is fluorescence imaging, and they can image synapses. So what you're seeing fluorescing in this image are proteins that are in the synapses, which are the locations where neurons communicate with one another. And basically, the brighter this is, the stronger the connection of these synapses is. And the tools that they have in place right now is good enough that it allows you to get a general understanding of more or less strengths at the population level of these synapses. And this is live imaging, so we can do this imaging while the mouse is alive. But it's still very limited if you want to say something very precise. For example, how many synapses are formed when a mouse is exposed to a certain stimulus? Or how does the population of synapses change? How do these brain circuitry gets reshaped when exposed to certain stimuli? So what we've done together with some collaborators is design AI algorithms, machine learning algorithms that can restore these images, which perhaps you can't appreciate very well from the slides, but to a level of quality that you would only observe if you were to sacrifice the animal and image the brain tissue ex vivo. But you can get virtually the same quality of image, virtually same SNR, and resolution that you would get ex vivo, but you get it to do it in vivo. And now, because the animal is in vivo, you can do cool things like count and track synapses longitudinally in studies. And so we can do things like literally have a mouse being exposed to stimulus and other mice in a control group, and detect which is the mouse that has actually undergone the stimulus and which one has not. We can do things like help pathologists. So say, something that pathologists do very often is giving a whole slide image like this, try to segment where the tumor is. And this is a very laborious and tedious and expensive task to do. So it would be fantastic if instead of having a pathologist annotate everything very carefully, they could just do some broad strokes. And then we would have a tool that would refine these into these way more accurate segmentations. And this is something that is done by a method that we developed. This is done automatically, and it's very, very close to the ground truth segmentation. And the methods that do this actually have not been trained on anything. They can train entirely on the annotations that are given on only these single slides. Or at the macro level, and this is some work that we've been doing together with people like Mike Miller and others, where you care about understanding and measuring the magnetic susceptibility of the brain. So this is in magnetic resonance imaging. You can try to quantify many things, but one of these things is magnetic susceptibility, which is the amount of it's the degree of magnetization that matter adopts when it's put in an external magnetic field. And this quantity is very interesting because it's not isotropic, so it's a little tensor, and this tensor has a direction. And this anisotropy of the magnetic susceptibility depends on the structures that you have in the brain. And so, for example, for myelin that is very structured, myelin is basically a layer of lipids that surround axons. It has a very structured shape. This has a very strong anisotropic component. And so if you could image this, you could use it to do tractography. You could use it to reconstruct the fiber tracks in white matter fibers in the brain. The problem is that to do this, you actually need to put a patient or a subject in an MRI scanner and literally have different acquisitions with their head at different orientations, which is very cumbersome, borderline impossible in a clinical setting. And so again, using tools of modern deep learning techniques, what we've done is we've been able to do this kind of reconstructions of tractography, of reconstruction of white matter fiber tracks, but reducing drastically the number of acquisitions that you need to actually perform in the scan. So all these are really cool applications that I work on with my colleagues who basically tell me about the needs for these tools. But of course, there are many things that we should also be very cognizant about. And a lot of my lab pays special attention to these kind of concerns. I wondered also, just for me to have a rough idea, who has seen this notice in this room? Okay, perfect. So about 50% of the people in this room have taken notice of this presidential order from last October. And as you can imagine, this technology being increasingly deployed in many settings also means that we need to be very careful about the way this is used, the degree of reliability of these algorithms, the degree of trustworthiness, the degree to which they are fair or unfair to different populations, and the degree of transparency and interpretability. This is not the only regulation body that is out there. This, in fact, has been a growing effort since 2015 or so. There are very interesting differences between regulations in Europe, regulations in the United States. And so in my group, we take basically inspiration from a lot of these needs and try to address them, or at least understand to what extent we can address them in a formal manner. So what I will tell you a bit in the rest of what's in the rest of this talk is some of these topics. I care very much about aspects of interpretability, aspects of inverse problems, as well as fairness and uncertainty quantification, mostly in medical imaging, but also generally. We won't have a lot of time, and so I will mainly focus on these two aspects, but I'll be very happy to comment further on other notions as well. By the way, feel free to interrupt me at any point if there are any questions. I'm happy to stop as much as necessary. Okay, so what is this question of interpretability? So let's say that I have a bunch of samples. These are images, these are blood smears. So these are microscopic images of basically drops of blood. And there are many cells in here. And some of these samples come from healthy patients and some come from sick patients. And I want to develop an algorithm that looks at these images and can tell me if a patient, for example, is sick. And we can do these things very well. By now, we can develop these algorithms that work very, very well. But in the end of the day, I not only care of just having a model that works well, I also care about understanding what is it about this image that is conveying the information that the patient is sick. So only slightly more formal, and we are going to build up in formalism as we go. I would like to understand if there is some little part of this image that perhaps is where the information about this patient being sick mostly concentrated. In this case, I know for a fact that this is true because in this case, the sickness comes from malaria disease, and malaria disease is actually characterized by the presence of certain proteins in a specific type of cells. So in this case, it's definitely very much localized. But I would like to discover these things automatically if I didn't know them. So there are many ways in which the community has framed these notions of interpretability, or at least in which the community has tried to answer these questions. There are many methods that look at notions of sensibility. So for example, if I have a model, I could try to ask what features in my input should I change if I want to increase my loss a certain direction. And that perhaps tells you something about this function. Or you can look at things like Shapley coefficients, an element of game theory that I will talk more in a minute. Or you can look at variation formulations and counterfactual explanations. Before I move on, so what most of the community sort of has done is come up with these sensitivity maps. This is, for example, for the family of methods that you see up above, sensitivity of gradients, where, for example, if I'm taking an image and I have a model that classifies the image as a person, well, these methods sort of mostly highlight these pixels, which is where the face of the person is located, and that conveys some sense of interpretability. These methods, based on sensitivity and gradients and so on, have a bunch of problems that I don't want to spend too much time on. They're very brittle, they're very subtle, and in fact, there are settings where these things are provably incorrect. So they're very limited, and we would like to be a little bit more thorough and be able to say something more about what these interpretability notions mean. So let's talk about Shapley values for a couple of minutes. So Shapley values is basically a concept that has nothing to do with statistical learning, is a notion that came out of game theory. And the setting is the following. Imagine you have a game, and a game is characterized by a set of players and a function, and this function goes from the power set of the players, so it's a function that takes in a subset of those players and outputs a value that tells me something about the game. So it's like the score that the subset of the players would receive if they were to play a game. And so you can ask the question, how important is every player in the outcome of a game? And it turns out that if you want these notions to satisfy a few axiomatic properties that you define, then the answer is unique and is given by expressions, this expression that you see here. What this is saying is the Shapley coefficient of the ith player is the sum over a bunch of subsets, and in each subset you evaluate the game considering the player and that subset, or the subset without the player. So for example, if I'm originally from Argentina, so let's say that I wanted to compute the Shapley value of Messi in a soccer game, then what you would do is you would play many games, and in each game you would take 9 players plus Messi versus the 9 players, or all possible subsets of 8 plus Messi and the 8 players, and so on and so forth. So in some sense, this is the marginal contribution of player I to each of these coalitions S, or each of these subsets S. This is very nice. It satisfies some properties that are sort of defined axiomatically, but the problem is, as you can imagine, I'm summing over all possible subsets, and this grows exponentially with the dimensions, or rather with the number of players I have. But that hasn't prevented people from using these ideas in machine learning. And in fact, as you'll see, they're useful. So how do we bring these notions of game theory to a machine learning setting? So in a machine learning setting, we have an input space, X. We have responses. Let's assume that they are binary for now, for simplicity. And I have a predictor that maps inputs to outputs. I will not assume anything about my input. You could think of this as an approximate, you think of this as a good predictor. So ideally, this would be something like the expected response given the sample that you get, but this won't be an assumption. Just think of this as a good predictor. So the first thing we need to do is, what does it mean to add players and subtract players? Because in the end of the day, these things are in Rn. They have n dimensions. So I can't just toss players out. I can't just take features out. So what we're going to do is given a sample in n dimensions, I'm going to construct, so this the little capital is an instance and the capital letter is a random variable. So I'm going to construct a random variable that has S of its features fixed by the observation that I was given. And the complement is going to be drawn from the corresponding conditional distribution of the data. Condition on having observed it. So basically what I do, if I want to create a lot of these variables x tilde s, is I see my observation, I fix these. These are all fixed. And then for the complement, I sample them from the distribution of my data condition on these variables being fixed. So the only thing I need to do this is a good approximation or a good characterization of this conditional distribution of my data. A very reasonable question would be, when would you be able to do that? That's a very complicated thing for high-dimensional data. That's true, but the good news is that we are getting better and better at sampling from these kind of distributions. So for example, here's an image, and here there's a subset of features, and I want to condition on this and sample from the corresponding conditional distribution. Fine, we have great models to do this now, and here there are a few samples that sample the rest, the complement of my features, conditioned on having observed these, and they all look pretty reasonable. Okay, so these are going to be our variables x tilde s. They all share in common the little s part. Okay, now that I have these variables, then I can tell you how to compute these Shapley coefficients in this setting. I will do exactly the same. Now, adding a player and subtracting a player is simply adding a dimension or not, in this sense. I will construct these random variables where I fixed s plus I versus I only fixed s. And I do this for every subset s. And these are random variables, and so I can, for example, put an expectation there. Okay. Again, this is great, but I have the same issue that I have exponentially many features on top of having to sample from this conditional distribution. Okay, what we're going to do now is notice that in many settings, there's a lot of structure in data that allows us to bypass these exponential bottlenecks, these exponential computational complexities that we have to compute these quantities. So on image data, what we are going to assume, and you might think a priori that this is a strong assumption, but I promise it's pretty weak. What we're going to assume is that my function is going to output 1 if basically there exists a subset of my features. There's one feature that conditions our response to be 1. Don't worry too much if this is hard to parse. All this means is that my response is going to be 1 if there is something in my image that I'm trying to find. So all these settings of like image classification or object detection, they all fall under this assumption. There's something in my image that is determining the class of the image that I'm predicting. In the case of these blood smears, this is in fact true because we know that specific cells condition the response of the patient being sick. So this is the case. If your problem satisfies an assumption like this, then it's great because then I know what to do and I don't need to pay an exponential price. All I can do is, given my feature vector, I can, let's say, divide it in 2. I will just have 2 players. I can compute the Shapley coefficient for these 2 players. This is still exponential, but in dimension 2, it's totally feasible. If these are 1, if both of these players are important, I get a half for each. Then I can subdivide further. The ones that are 0 will always be 0 because of this assumption. And the ones that are 1, I can cascade further. And I hope that you can see that now we've broken the problem in a combinatorial problem in n dimensions to basically log of n problems of fixed dimensions. We decouple the dimension of the problem from the computational complexity of computing these Shapley values. So it's not hard to see that now this doesn't run in exponential time. This actually runs linearly in n. And under this assumption, whenever you have objects that you're trying to detect, the Shapley coefficients that you recover are actually the correct Shapley coefficients that you would have computed had you run your algorithm, your naive algorithm, let's say, exponentially number of times. So this actually works really nice in practice as well. So for example, for these cases, well, remember what we're trying to do is detect cells, right? So my learning algorithm only has access to the label of the image. It's never seen what a sick cell looks like, does not know anything about that. So I can train a predictor that predicts this and then use this approach to find where the important features are and detect these sick cells automatically. So this is the kind of things that we can give you. These are methods that are also based on Shapley coefficients, based on some other naive approximations that basically take way too long, and that's why you don't see anything here. And these are sort of gradient-based and sort of linear approximations. That they're all kind of messy. You can be more quantitative. These things work basically faster and more accurate than any of the other methods. So here you have F1 score and computational time. And so these methods typically do the best in terms of accuracy, as well as orders of magnitude faster than other Shapley computation steps. Okay, so far what we know is, okay, we have this notion of Shapley coefficients. They are kind of nice, they come from game theory. We can compute them efficiently sometimes. But it's still kind of weird, right? Because we are using concepts of game theory to apply them to a statistical learning setting, right? We are presuming that these features are players and that they're playing a game, but that's kind of anthropomorphizing. It's kind of weird. And so what we're going to try to do now is understand what these things actually mean. If you go to the statistics literature, a totally feasible definition of what is an important feature is something like this. I would say that my features S are important, or rather in this case, non-important, if once I condition on all the other features, I don't have any more information about the label, right? So features S don't contribute, basically it's independent of my response the moment I've seen the other features. So this is nice because it's posed in terms of a hypothesis test, so I can test for this. And if I reject, for example, at a certain level of significance, I can conclude that features S are important, and I have an associated failure probability for this. Yes. Here should be S. Thank you very much. Yes, this is just the index of the test I'm running. Yeah, this should be S. Thank you. Yeah, of course. But if I fix S in advance, this would be a notion of importance for what it means for features S to be important. You're right. And in case you're not used to the notation, this is basically what this means is that these conditional distributions basically are, you can drop the conditioning of excess. So Y condition on everything is the same as just conditioning on the copy. Okay, so we want to bring these notions to this setting of modern machine learning predictors where we are actually seeing a specific sample. This is over a distribution, it's a population. So what we're going to do is the following. We're going to say that a specific feature I is not important with respect to another set S if I look at the distribution of my responses when I fix S and that feature. If this distribution doesn't change, if it is the same in distribution as that of my outputs when I'm only conditioning on S. If the distributions of my predictors doesn't change the moment I add I to S versus when I don't, then I'm going to conclude that my feature I is not important. And if I manage to reject this null hypothesis, then I will assert that I is important with respect to S. This is more intuitive than what it looks like, I promise. So for example, going back to the case of the cells, let's say that I have 4 features. In this case, the features are these 4 quadrants. Here, the response is 1, and I know that it is 1 because this cell is actually the 6th cell. So this 6th cell is conditioning my response, but I don't know this in advance. So I have 4 features. If you run this test, if you test for this hypothesis, this null hypothesis, you will find that, first of all, if I fix all of these quadrants, then the response is uniformly 1. It's just a delta at 1. If then I fix these 3, but I sample these quadrants from the conditional distribution, well, sometimes there's going to be a 6L, sometimes there won't be a 6L, and therefore the distribution of my predictor will change from that delta at 1 to be, basically it will be 2 delta 0. And so in this case, you would reject this null hypothesis, and therefore you will conclude that this quadrant is indeed important. So a reasonable question is, okay, can you test for this? So assuming that you can sample from these conditional distributions, the answer is yes. You can have, we have an algorithm that basically samples and returns a p-value for this test, the valid p-value, which is fine, but this is perhaps the more interesting observation. Nothing has changed. This is the same null hypothesis that I have. Take the Shapley coefficient for feature I. It's a bunch of sums of these expected things, these expected differences. Call this difference gamma I. And PSI is the p-value that I received from the test for that null hypothesis. Turns out that this p-value is upper bounded by these terms in the Shapley coefficient. And what this means is that if a Shapley coefficient is high, close to 1, what does that even, what does it mean for a feature to have a high Shapley coefficient? Well, it means that each of these terms are very high, they're close to 1. And if these terms are close to 1, these p-values are very small, which in turn means that I can reject this null hypothesis. So in other words, this is telling us what does it mean for a feature to have a high Shapley coefficient from a statistical point of view. It tells us that things that have a high Shapley coefficient are important in this statistical sense. And it allows us to, for example, do false discovery rate control on the important features that we are now reporting. Okay, this is not the only notion of importance that you can use. There are many notions out there. For example, something that you would require is for your features to be sufficient for a problem, sufficient for a task. So what does it mean? It means that if so a feature S, a set of features S, is epsilon sufficient. If I condition on it, then the response doesn't really change. Think of epsilon as being very small. So as long as I'm conditioning on S, which has these important stuff, then the response of the predictor doesn't change. This is the example of the 6 cells, for example. If I'm conditioning already on the 6 cell, whatever I put on the rest doesn't change the output of my predictor. Now, you could ask instead for your features to be necessary. And this is similar, but it's different, because for a subset S to be epsilon necessary, what I want is that if I drop them, so I'm conditioning on the rest, if I drop this set of features, then I'm just predicting base rate. Then I have nothing better to tell you. I'm just giving you a coin flip on the response. So this is what actually many people refer to as a preservation game. I want to preserve features so that my predictor doesn't change. This is what often people refer to as a deletion game. I want to delete features to see how I can perturb my output the most. It's very important, though, to understand what these things mean and how they're different. So here's an example. I have brain CT scans, and I'm developing a predictor that predicts if a patient has a brain hemorrhage. And in this particular case, there are like at least 5 bleeds in here. You train the model predicts very well, performs very well, high accuracy. Then I want to understand what is it that this model has met. If you compute these things that I'm not telling you how to do, but at least I'm showing you an example, you will detect these two bleeds as being sufficient. In other words, if I condition on only these two bleeds, the model will say that there is indeed hemorrhage. But these are not necessary. I can compute this necessary set, and it's going to be in this case a superset. And these are necessary because if I don't have these, then the model doesn't predict that there is a hemorrhage at all. So I work closely with radiologists, and this is really important to them. They are very interested when they see these examples for the following reason. There are many aspects in these images that are actually very highly correlated with hemorrhages, brain hemorrhages. For example, there's hematoma, there is bleed externally outside of the skull that you can barely see. But when radiologists see these, it's very, brain hemorrhages is a main suspect. Yet none of these things appear in as far as this model is concerned, appear in those as being sufficient features, which can be bad or good depending on what you want your model to do. But at least it's very important to understand what your model is picking up as sufficient and necessary features. One last observation about this. There's no need for you to pick one or the other, either necessary or sufficient features. You could just say, I'm going to combine these two things, and I'm going to require features to be both sufficient and necessary. And we can combine them with a parameter alpha between 0 and 1 that will tell us how I want to trade off sufficiency and necessity. Turns out that when alpha is a half, so these features are as sufficient as they are necessary, these features are actually the same features that maximize the Shapley coefficient in a two-player game. So these features S give me a partition of my features into S and S complements. The claim is that searching for this partition that gives me the necessary and sufficient features is the same as finding the player in this two-player game with the largest Shapley coefficient. Okay, I'm going to change gears slightly and move to inverse problems, where again we care very much about interpretability, but now the setting is different because we're not predicting. Oh yes, of course. Please, by all means. No, please. Great.
Versus the lack of that feature.
Yep.
And if I use the Messi example, you have to play with 11 players.
Correct.
You cannot play with 10.
Yeah.
Or if you are looking at the image,
Exactly right.
there has to be some math.
Exactly.
So I wonder whether there are metrics where you are replacing that part of the image or the feature with some random feature and compare the specific feature that you're considering versus a random replacement. Are there notions of this type of?
Yes, precisely right. So correct. I can't just drop players. So what I do is I can ask what is a random player that would come in its place for this distribution. So for example, in the Messi player, in the Messi setting, I'm going to drop a player. I'm going to sample a random player in this place. Okay, but it has to be a feasible play. It has to be something that is likely in this distribution. For example, I could not pick a player from Japan's national league, right? Because it wouldn't be likely. So indeed, we construct these random samples where we fixed a set, and the others are sampled at random from the distribution.
And another question. So here you're, in the image example, you're considering as features, we call features a part of the image,
Yeah.
right? And you are looking at the contribution of that.
Correct.
But if you are using any neural network architecture, there would be some combination of parts of the images that are coming from many different parts of the images that may form an informative feature.
Very nice. Yes.
So these
Correct.
combinations,
Correct. Absolutely. Absolutely.
how are they
Excellent.
are considered?
Yeah. Beautiful. I really like the question because it.
And maybe just to add something to that, I wonder whether using visual transformers, where the parts of the images get separated and getting something from the attention layer, whether that gives you some information.
Great. I really appreciate the question because it's something we've been asking ourselves also. So you would have noticed that I'm not assuming anything about it. And because I don't assume anything about it, then the only thing I can ask for is how do each of these input features tell me something about the response? And I'm ignoring all of what you're saying. What we're doing now is actually not looking at attention layers or anything like any structure of the network specifically, because then we are tying ourselves to a specific architecture. But instead, what we are doing is finding ways of posing these similar questions of conditional independence these similar questions of conditional independence, but in a semantic sense. So if I have features that are extracted and these features convey specific concepts, so imagine that you have access to a concept bank of texture or color or, I don't know, patterns that you might see. Then you can, in principle, and we have preliminary results on this, on asking these questions, but at a semantic level. And now the answer is not given in terms of the individual pixels, but rather in these abstract notions, which are much more human understandable. So indeed, that's a great question, and we're working on that. By the way, it's not obvious how to extend these things and have tests that compute these p-values in a valid way for these semantic concepts. But it's cool stuff, and we hope to have a paper out on this soon. All right, so inverse problems, unlike these prediction problems, are settings where I have some ground truth vector that I don't observe, and instead I observe some measurements that come from it. And there's some noise to it, and then this need not be linear, some forward operator. And this is ubiquitous in imaging. All the time you're trying to reconstruct something from some partial noisy observations that you get. Probably if you're not a student, then the way that you would do this 10, 15, or 40 years ago is by writing this variational problem where you might ask to find, I'm sorry, it should be X, to find an X that is likely under your data, so that if I push it through my forward operator, I get close to the data that I got, to my measurements. But this problem is ill-posed. Typically, there are infinitely many solutions to this problem. And so I regularize it by adding a regularizer function that tells me more or less how likely is my X under some prior distribution. And this is nice in the sense that, if you look at this from a Bayesian perspective, then this is actually computing the map, the maximum a posteriori, given the point that maximizes the posterior probability of the unknown given the measurement. And this is true if this regularizer is minus the log prior, minus the log P of X. Okay, so in traditional methods, what would you do? You would just do this. You would pick your regularizer, for example, something with a small TV norm or something. Hopefully that regularizer of yours is convex, because if it is convex, then you have convergence guarantees for this problem. And then you could, run it with a bunch of algorithms, for example, proximal gradient descent, where I just take a gradient with respect to this convex term, and I compute the proximal over my regularizer. In case you don't know what a proximal operator is, that's totally fine. The proximal operator for a function R is simply this, is the vector that minimizes the sum of an L2 and the regularizer. So it's a very similar problem. The only difference is that there's no A matrix. It's just finding the proximity point that minimizes this regularizer. All of this machinery has been used in signal and image processing for 30, 40 years. So there's a nice observation that was done about 10 years ago that this prox is actually a denoiser. is also computing a denoiser, right? I have no forward operator. I'm just searching for an image that is close to my measurements, but is also likely under my priors. I'm basically trying to denoise. If you assume Gaussian noise, this is nothing else but the Gaussian likelihood, right? And so you're just doing Gaussian denoising. And so this nice paper basically said, hey, if this is computing a denoiser, I can just plug in any denoiser out there and just plug it in here. And now I will have this like general purpose algorithm to solve inverse problems. All I need is a good denoiser. And a good denoiser can be any off-the-shelf, anything from a CNN to diffusion model. And so this works really well in practice, but obviously by plugging in these very good performing methods, we lose something very important. We knew that all this was good as long as these functions were proximal operators, but now we just plugged in a function and we have, who knows if this is a proximal for any function, right? And so there are three questions that we would like to answer. First, when can I train a neural network and be sure that this function is actually a proximal operator? The second question is, a proximal operator for what? And I really want to know this because if I'm training this from data, I want to learn what is the regularizer that I'm learning adaptively from data. This is basically telling me what is good and what is bad about the distribution of data that I'm seeing. And in particular, I don't care about learning any regularizer. I want to learn the correct regularizer in some sense, which is precisely the minus the log of the prior. So we have answers for these three. I'm going to give you a glimpse of these answers. The first one is pretty easy. Turns out that there's this very beautiful work by Remy Grimombal and collaborators. And they give us basically a complete characterization of proximal operators. So the statement is that any function f will be a proximal operator for some function r if and only if there exists some convex function, C, psi, so that f is a gradient of, or isn't subdifferential of psi. So this is a picture that you should keep in mind. I have a function. This function is a prox of some regularizer. This will be true if and only if there exists some convex function, so that when I derive it, I get this thing. There's some very cool things about this. One of these is that R, my regularizer, need not be convex. Typically, when we define proximal operators, we restrict proximal operators to be proximals for convex functions. This does not need to be the case. So potentially, we are going to come up with regularizers that are non-convex. So the problem now reduces to how can I train a function, a neural network, that is a gradient of a convex function. Turns out we can do that because there's a community that cares about finding parametrizations for convex functions in terms of neural networks. This is one such work, the work by Zico Coulter and his students. And so you can have networks that are convex with respect to their input. So we just take some of these networks and then compute the gradient map of that function. And that's it. Then by construction, our function f will only be able to represent proximal operators. Yes? Great question. So it's very good question. If this prox was the prox of a convex function, then it is contractive. But in this case, I can have a prox that is non-contractive because the regularizer R is non-convex. So we are asking even less than being contractive. Asking for contractive of the operator is too much. This is more general than that. Yes, people have done this. And so, for example, one of the reasons you care about contractive operators is because you can show convergence guarantees with them, because it's nice. At every step, you don't blow up. This, as I said, on the one hand, is more general. It includes contractive operators, but it's not restricted to them. But, and I'm not going to talk about them, if you do this though, you also gain a lot of very nice convergence guarantees. Because you, I mean, fine, it's not constructed, but there is many other properties that you can use because your function is approximate. So why do you care for it being approximal? I care because I want to have some notion of convergence guarantees, which I can still do in this case. And moreover, because I want to characterize this prior, right? I'm learning this from data, and I want to know that my function, my neural network is actually computing approximal with respect to that prior that I just learned from data. It's a very good question. Let me skip to question 3. Fine, we can have these functions that compute proximal operators, but I don't want it to be the proximal for any function. I want it to be the proximal for my log prior. Naturally, I don't have my P of x. I don't have an analytical distribution, an analytical expression for the distribution of natural images, but I can sample from it. And so the strategy will be, and just as a reminder, what we want is this function f to be the prox of r. And if you remember from a couple of slides ago, this indeed boils down to the map, the maximal a posteriori estimate of x given y. So what we're going to do is we're going to have noisy measurements. So x comes from my P of x, and v comes from a Gaussian. And I'm going to try to learn a function that basically denoises my observations. Given y, I'm going to try to learn a function that gives me a good approximation for x. And in particular, I'm restricting f to be a prox, and now I know how to do it. It has to be the gradient of a convex function. Okay. The question, though, is what loss function are you going to use here? Which is non-trivial, because, for example, if you just use an L2, then the solution of this is just a conditional mean, which is not the answer you want. Remember, we wanted the map. We want the maximum of that posterior, not the mean of that posterior. If you use an L1, you recover basically a generalization of the median, which is still not what we want. So here's a loss function. We call it proximal matching loss. It's kind of like a relaxed delta function. It doesn't really matter what the expression is. In fact, it's more general than this. But here's the statement. If you use this loss function, and this loss function is controlled by a relaxation parameter, gamma, if you minimize this in the limit as gamma goes to 0, so as this becomes thinner and thinner and thinner, and here we are minimizing the actual risk, so no finite samples, then the solution that you get actually computes the correct prox. It computes the maximum of that posterior, which is the proximal of the log prior, scaled by sigma, which is the noise that you had in the measurement. So all this is saying is that this strategy works in the sense that you will recover the correct proximal operator as long as you use the right loss function. And the right loss function to use is this function here. The details are not so important, but in the limits, as this gamma goes to 0, you will recover the proximal of the prior of the data. Okay, just to finish, let me give you a couple of examples. Remember, I started this, and in fact, the motivation is I want to compute proximals because I want to be able to characterize what the regularizer that I've learned is. I'm not telling you how to do it. It's easy. It boils down to a linear program. But let me just give you an example. We take data that sample from a Laplacian, and we add Gaussian noise. Why a Laplacian? Because I know exactly what the prior distribution of a Laplacian is. It's just an L1 norm, and I know how to compute the proximal of an L1 norm. It's just a shrinkage factor. Okay, so I'm going to train my network to denoise Laplacian data from Gaussian noise, but I'm not assuming anything about the distribution of the data. I'm just training the model in this way. After I'm done training, I evaluate the function that I obtain. And in dotted lines, you see the correct proximal operator, which is its shrinkage. If you use an L2 or an L1 norm, you recover things that are not quite precise, because indeed they're not the maps, they're the conditional mean and conditional median. But if you use these proximal matching laws, as gamma goes to 0, then you will indeed recover the correct proximal operation. And I can now go back, I can query what is R of X, what is my regularizer. And indeed, if you compute it, you'll see that you will recover a very, very good approximation to the precise L1. So it's kind of like doing density estimation, but by modeling the proximal of the density rather than the density itself. Of course, you can now train this on many things. Here's just a demonstration on digits to show that if I'm done training, I can now query this regularizer and literally see how likely is this under my prior, because this is what the regularizer does, right? If the value is very low, the value of the regularizer is low, that means that this is likely under my prior. So when I have very little noise, the value that I obtain is very small. As I perturb with noise, these samples are less and less likely under my data distribution, and indeed, the value of the regularizer shoots up. I mentioned before that the regularizer need not be convex. Here's a proof of that, basically, because if I take two digits that look nice, the value of the regularizer is small. If I take a convex combination of these two digits, these things are definitely not likely under my prior because they don't look like real digits. And indeed, the regularizer tells me that they are not likely under real prior. If the regularizer had been convex, this would not be the case. These would all be done. These are just sort of toy-like settings that allow us to understand what has happened, but nothing prevents us from applying these to real problems. So here is a setting of deblurring and denoising. And you can plug this. As I said, this is a plug-in method. It's just a denoiser that you can use to solve any inverse problem, but with the added benefit that you know for a fact that is computing the proximal of a function, and in particular, you know that that function is approximating the prior distribution of the data. And you can look at the more detailed results in the paper, but by and large, this works as well or even better than methods out there, but has these extra nice guarantees. And of course, this is particularly important in settings where you really care what these distributions are. So in this case, for sparse view CP and for compressed sensing, these things work really well, but now we can actually query these densities that we've known. That's mostly what I had. I wanted to comment quickly on aspects of fairness, but I don't really have time, so I'm just going to conclude. I personally think that the vast deployment of these tools, and particularly in the healthcare setting, is really cool because it opens up a bunch of problems that we don't yet know how to solve. And in particular, I would stress that in solving these problems, we really need to come up with precise definitions that then allows us to understand really what we mean when we say that something is interpretable or that something is fair. I'll just end with this extract from that presidential order that you saw before, where President Biden literally writes that in the end, AI reflects the principle of the people who build it, the people who use it, and the data upon which it is built. I thank my collaborators. The work that you saw comes from this group of folks, the students and collaborators. If you liked what you saw, it's probably because of them, and if you didn't, it's probably because of me. And I would love to take more questions if you have any.
So is it related to the knockout idea of a canvas? How is that different from the knockout?
Yeah.
They can also provide p-value.
Correct.
P-value.
Well,
so how is that? You have a different strategy for p-value?
Yeah, that's a good question. So knockoffs is an alternative way in basically rejecting the null that I described, but without providing p-values. Because it has basically this knockoff idea, which provides these false controls that you can use to basically control which ones you report. So it has false discovery rate control without computed p-values. However, the definitions of what it means for something to be important is precisely, it's inherited from the very same paper. In the knockoff paper, they actually say in passing, basically, well, if you really wanted to compute p-values, you could run this test, and they call it a holdout randomization test. And the procedure that we have is a version of that holdout randomization test. So it's very much related in spirit, but the methodology is different. We're not doing knockouts, but it's a very good question.